Welcome viewers, we are now going to discuss the fourth episode on organometallic compounds. In the earlier three episodes, we have discussed the preparation and methods of and various reactions undergone by organometallic compounds. Under this category, we have included the Grignard reagent, which are organomagnesium compound, and we have also discussed organo-zinc compounds. Now, in the present lecture, we will discuss the introduction to organolithium compound, then bonding in organolithium compound. After that, we will discuss preparation of various organolithium compound and then the reactions of organolithium compound. Under the category of reactions of organolithium compound, we will discuss these compounds as Bronsted bases. We will discuss their reaction with active hydrogen containing compound. We will discuss their reaction with carbonyl compounds. We will also discuss the preparation of alkynyl organolithium compound and their use in the synthesis of alcohols. Then we will discuss their reaction with oxygen, with epoxides, with esters, with carbon dioxide. Then we will discuss retrosynthetic analysis, in which we will discuss the planning of synthesis of primary, secondary and tertiary alcohols by retrosynthetic analysis. To start with organolithium compounds, organolithium compounds are the organometallic compounds having carbon lithium bond. As you can see here in these models, this is the alkyl group and this is lithium atom. So, the carbon lithium bond is present in methyl lithium, in ethyl lithium also, and similarly here in case of normal propyl lithium, this is the carbon lithium bond. Organolithium compound behave in the same manner as Grignard reagent, that is, they provide a nucleophile or carbanion. They are, however, more reactive than Grignard reagent. The reason is that the lithium is more electropositive compared to magnesium. They are used extensively in organic synthesis. Organometallic compounds are usually kept in organic solvents due to their very high reactivity, especially with water and oxygen. Organolithium compounds and organomagnesium compounds have a sigma bond between a carbon atom and the metal. These carbon metal bonds are very polar covalent bonds due to electropositive character of the metal. The organometallic compounds have carbanionic character. The ionic character increases with increase in electropositivity of the metal. Organosodium and organopotassium compounds have ionic carbon metal bond, whereas organolithium and organomagnesium compound have polar covalent carbon metal bond. It is the carbanionic character of these compounds which is responsible for their usefulness as synthetic reagents. We will now discuss the preparation of organolithium compounds by the reaction of alkyl halide with metallic lithium. Organolithium compounds may be prepared by the reaction of alkyl halide with lithium in dry ether at -10 degrees centigrade. The reaction is carried out in inert atmosphere of nitrogen. Here it is methyl iodide reacting with lithium at -10 degrees centigrade, formation of methyl lithium takes place. The reaction of alkyl halide with lithium is an oxidation reduction reaction. Group 1 elements like lithium or sodium are powerful reducing agents. Among alkyl halides, alkyl iodide react fastest, followed by alkyl bromides and then alkyl chlorides. Tertiary butyl chloride reacts with lithium to form tertiary butyl lithium. As you can see here, it is tertiary butyl chloride having a tertiary alkyl group associated with chlorine. This reacts with lithium and forms tertiary butyl lithium in good yield. Lithium reacts with vinyl chloride and bromobenzene to form corresponding vinyl lithium and phenyl lithium respectively. The reaction, however, is relatively slow. The reason of the slow reaction is the carbon bonded to halogen is sp2 hybridized in case of aryl halide and vinyl halide. You can see here that this bromine, this halogen atom is bonded to sp2 hybridized carbon here, and that is why this reaction is a bit slow. There is formation of phenyl lithium when bromobenzene reacts with lithium in diethyl ether. You can see here that we require a bit higher temperature, whereas in the earlier case the temperature required was only -10 degrees. The solvent used for the preparation of organolithium compounds are pentane, hexane or diethyl ether. The solvents should be anhydrous. Do you know what is the reason behind it? The reason is that even the trace amount of water or alcohol reacts with lithium and form insoluble lithium hydroxide or lithium alkoxide that forms a coating on the surface of the metal and prevent it from reacting with alkyl halide. Also, since organolithium compounds are strong bases, they react rapidly with even the traces of proton sources and form hydrocarbons. Reaction of alkyl halide takes place on the surface of lithium metal, and in the first step of mechanism of reaction, an electron is transferred from lithium to alkyl halide. As you can see here, this is lithium metal and this is alkyl halide. One electron from lithium has been transferred to the alkyl halide. There is generation of an anion radical along with lithium cation. In the next step, alkyl halide, after gaining an electron, becomes negatively charged and is called anion radical. The extra electron occupies an anti-bonding orbital. In the second step, this anion radical dissociates into an alkyl radical and halide ion. As you can see here, this is anion radical. Upon dissociation, it generates an alkyl radical and halide ion. In the third step, the alkyl radical rapidly combines with lithium metal to form organolithium compound. You can see here that alkyl lithium has been generated. The carbon of organolithium compounds have appreciable carbanion character. The carbanions are extremely strong bases as their conjugate acid, that is the hydrocarbons, are very weak acids with pK values in the range of 25 to 70. You can see here that these carbanions very easily are converted into the corresponding hydrocarbon by the abstraction of proton from weak acid water. There is generation of this hydrocarbon which is a weak acid and hydroxide ion which is a strong base. We will now discuss a few reactions where organolithium compound act as Bronsted bases. They are strongly basic and react with weakly acidic proton donors like water, alcohol, carboxylic acids. A proton is transferred from the hydroxyl group to the negatively polarized carbon of organometallic compound to form a hydrocarbon. As you can see here, this is the organometallic compound. The proton from the alcohol has been transferred to the organometallic compound and there is formation of a hydrocarbon. Organolithium compound act as bases. This can be seen in the following example where butyl lithium reacts with water to form butane. Here this is butyl lithium. It abstracts a proton from water molecule and forms butane and there is formation of lithium hydroxide. Another example where organolithium compound shows its character as base is the reaction of methyl lithium with ammonia. There is generation of methane and lithium amide. You can see here that one of the hydrogen from the ammonia molecule has been shifted or replaced this carbon lithium bond. There is formation of weaker acid methane starting from methyl lithium. Water in the same manner reacts with methyl lithium and forms methane. So, any compound which has replaceable hydrogen or wherever there is a possibility of transfer of proton from that molecule to the carbanionic alkyl lithium compound, the corresponding weaker acid will be formed. Water being a stronger acid than alkane can remove alkane from its salt. This is the salt of alkane and alkane has been removed from its salt by the water, which is a stronger acid as compared to methane. In this example, ethanol reacts with methyl lithium to form methane and lithium ethoxide. Alcohol, being a stronger acid than alkane, removes alkane from its salt. So, in this example also you can see that ethanol has an active hydrogen which can be replaced by this methyl lithium for the generation of a weaker acid methane during the process. Similarly, in this example we have used acetic acid which also has an active hydrogen. Methyl lithium reacts with acetic acid, forms methane and lithium acetate. The carboxylic acid is a stronger acid than alkane, and that is why it can reduce alkane from its salt. Here is an example where the reaction of 3-methyl cyclohexyl lithium with water is taking place. This is 3-methyl cyclohexyl lithium. When treated upon with water, it forms methyl cyclohexane. Now, this 3-methyl cyclohexyl lithium can be prepared from 3-methyl cyclohexyl bromide by treatment with lithium in diethyl ether. That is, this first reaction is the preparation of organolithium compound, and then second step is the reaction of organolithium compound with water molecule which contains active hydrogen. As a result, there is formation of an alkane. Here again, water being stronger acid than alkane can remove alkane from its salt. Now, the reaction of organolithium compounds where they are utilized for the synthesis of alcohols. Organolithium compounds react with carbonyl compound in the same way as Grignard reagent do. Organolithium compounds, however, are more reactive. You know the reason already. Organolithium compounds are more reactive because lithium is more electropositive than magnesium. Carbon lithium bond is more polar than carbon magnesium bond, and that is why the nucleophilicity of the carbanion generated by organolithium compound is much more compared to organomagnesium compound. Now, with formaldehyde, primary alcohol is formed. With other aldehyde, that means the aldehyde other than formaldehyde, a secondary alcohol is formed, and with ketones, tertiary alcohols are formed. Now, in this particular example, we have started with an alkyl lithium and a general formula for the carbonyl compound. This can be aldehyde or ketone depending upon the substitution at this carbonyl carbon. Now, when alkyl lithium reacts with aldehyde or ketone, it undergoes reaction to form first lithium alkoxide, which upon hydrolysis forms corresponding alcohol. Now, depending upon the nature of carbonyl compound, the final product, that is alcohol, is formed. Say for example, these two hydrogens here are H, then this aldehyde will be called formaldehyde, the product will be a primary alcohol. If one of the two substitutions are hydrogen, then it will be the other aldehyde other than formaldehyde, and then the product formed will be a secondary alcohol. And in case both the substitution on this carbonyl carbon are alkyl groups, then the product formed will be a tertiary alcohol. We will discuss this with the help of appropriate examples in the forthcoming slides. Now, first of all, the reaction of organolithium compound with formaldehyde. Formaldehyde reacts with organolithium compound to give addition product which upon protonation forms primary alcohol. With methyl lithium, formaldehyde forms ethyl alcohol, which is a primary alcohol. This is formaldehyde reacting upon with methyl lithium to form this lithium alkoxide, which upon protonation forms ethyl alcohol, which is a primary alcohol. So, starting from formaldehyde, we are getting a primary alcohol. Then the reaction of organolithium compound with aldehydes other than formaldehyde. For example, acetaldehyde or higher aldehyde react with organolithium compounds to give addition product which upon protonation form secondary alcohol. With methyl lithium, acetaldehyde forms isopropyl alcohol, a secondary alcohol. Here this is acetaldehyde and this is methyl lithium. Upon reaction they form isopropyl alcohol, which is a secondary alcohol. Now, the reaction of organolithium compound with ketones. Ketones react with organolithium compounds to give addition product, which upon protonation form tertiary alcohol. With methyl lithium, acetone forms tertiary butyl alcohol, which is a tertiary alcohol. Here this is acetone, this is methyl lithium. Upon reaction they form tertiary butanol or tertiary butyl alcohol, which is a tertiary alcohol. Here is another example where you can see this is cyclopropyl lithium reacting upon with 3,3-dimethyl 2-butanone. When this reaction takes place, this is the alkyl lithium part and this is the ketonic part. So, the final product should be a tertiary alcohol, and you can see here this product is a tertiary alcohol, can be named as 2-cyclopropyl 3,3-dimethyl 2-butanol. Now, with this particular example, we can see that we can prepare compounds, quite complex alcohols with the help of these organometallic compounds. Vinyl lithium reacts with benzaldehyde followed by acidic hydrolysis to form 1-phenyl 2-propene 1-ol, which is a secondary alcohol. You can see here this is vinyl lithium reacting upon benzaldehyde to form a very complex secondary alcohol. Another reaction undergone by organolithium compound is in the preparation of alkynyl organolithium compound. Actually, alkynyl organolithium compound are prepared by a route different from those used for organometallic compounds. Since the carbon hydrogen bond here is acidic in nature, the terminal alkynes react with strong bases like butyl lithium and form alkynyl lithium compounds. The active hydrogen may also be replaced by Grignard reagent and sodamide. So, here you can see that this is a terminal alkyne and the proton attached to this triply bonded carbon or sp hybridized carbon is quite acidic in nature, and when it is made to react with normal butyl lithium, which is a strong base, then a simple acid base reaction results in the formation of alkynyl lithium compound, where the lithium is attached to this alkynyl group. This alkynyl group is a very important group because it can be used for a number of syntheses, which we are going to discuss in the next slide. Alkynyl lithium compounds upon reaction with ketone form tertiary alcohol. For example, 1-hexyne reacts with butyl lithium to form lithium hexyne, which reacts with acetone to form the lithium salt of 2-methyl 3-octyne 2-ol, which upon acid hydrolysis form 2-methyl 3-octyne 2-ol, a tertiary alcohol. Here you can see this is 1-hexyne having an acidic hydrogen, a terminal alkyne, reacting upon with normal butyl lithium forming this alkynyl lithium, which reacts with ketone acetone and generates a tertiary alcohol. So, a very complex tertiary alcohol molecule can be generated by these sequence of reactions. A few more reactions undergone by organolithium compounds will be discussed now. One of them is reaction with oxygen. Alkyl lithium compound react with oxygen to form hydroperoxides. Here it is normal butyl lithium reacts with oxygen to form this hydroperoxide. When organolithium compounds react with epoxides, they form alcohols. Butyl lithium reacts with ethylene oxide and forms 1-hexanol. It is important to note here that 2 carbons are added during the reaction. See, in this reaction we have started with butyl lithium, we have treated this butyl lithium with epoxide or ethylene oxide. Now, when the reaction has taken place, the product formed is a primary alcohol, but in the starting material we had only 4 carbons and in the product we have got 6 carbon. So, the beauty of the reaction is that we can add 2 carbon atoms directly via this reaction of alkyl lithium with ethylene oxide. Now, if ethylene oxide is a substituted ethylene oxide, say for example, we treat this normal butyl lithium with 2,2-dimethyl oxirane. Here this is a substituted epoxide or substituted oxirane. When we undergo the reaction, this route followed will be the same. The product formed will be a bit more complex formed structure is formed over here, starting from normal butyl lithium and 2,2-dimethyl oxirane. The product formed is 2-methyl-2-heptanol, which is a tertiary alcohol. Organolithium compound react with esters also and form tertiary alcohol. Ethyl acetate react with methyl lithium and forms 2-methyl-2-propanol. Here you can see this is ethyl acetate reacting upon with methyl lithium, and there is formation of this ketone. The reaction does not stop here. Starting from ester, we have landed up into the formation of ketone, but the reaction does not stop here. Another molecule of methyl lithium reacts at the reactive site, that is the carbonyl group, and there is formation of tertiary butanol. Organolithium compounds react with carbon dioxide to form lithium salt of carboxylic acid, which upon protonation forms carboxylic acid. Methyl lithium reacts with carbon dioxide to form ethanoic acid. As you can see here, this is methyl lithium reacting upon with carbon dioxide. This is the carbanion which attacks the carbonyl carbon over here, formation of lithium salt of acetic acid, which upon protonation forms acetic acid. 2-methyl-propanoic acid may be prepared from propene and carbon dioxide by following this sequence of reaction. This is propene reacted upon with hydrogen bromide. By application of Markovnikov addition rule, it forms 2-bromopropane. This 2-bromopropane reacts with lithium in presence of ether and forms isopropyl lithium. Isopropyl lithium then reacts with carbon dioxide and generates 2-methyl-propanoic acid. So, by adopting appropriate starting material or by starting with right starting material, we can land up into the preparation of our desired product. We will now discuss retrosynthetic analysis. An important feature of planning a synthesis is reasoning backward from the target molecule to suitable starting material. E.J. Corey of Harvard University developed a systematic strategy for planning the synthesis of a target molecule, and this is called retrosynthetic analysis. This is very important, and he got Nobel Prize also for this development in the year 1990. In the retrosynthetic analysis, the symbol used to indicate a retrosynthetic step is an open arrow written from product to the suitable precursor. Now, we will discuss the planning of the synthesis of alcohol by retrosynthetic analysis. First, we have to identify the suitable carbonyl compound and the organometallic compound. In the first step, locate the carbon of the target alcohol which bears the hydroxyl group, because this carbon is originated from the carbonyl carbon. As you can see here, that this carbon is attached to oxygen or the hydroxy group. So, this part of the molecule, whether this part of the molecule or this part of molecule, will be originated from the carbonyl compound. In the second step, mentally disconnect a bond between the carbon attached to hydroxyl group and one of its attached group other than hydrogen. The attached group is the one that is to be transferred from organolithium compound. You can see here that in this particular molecule, if we disconnect this carbon bond, carbon and R bond, then this part of the molecule will come from the organolithium compound. In step 3, the two fragments, that is the carbonyl compound and the organometallic compound or the carbanion, are identified. Like for example, in this particular case, we can say that this part of the molecule coming from organometallic compound and this part of the molecule is coming from the carbonyl group. So, we can generate organometallic compound from this alkyl group, and this is the part coming from the carbonyl compound. In the last step, the synthetic route can be readily determined where a carbonyl compound reacts with organometallic compound to give desired alcohol. So, we can generate this alkyl lithium here, a carbonyl compound reacting upon in diethyl ether followed by protonation to give the desired alcohol. Now, we will discuss the planning of synthesis of primary alcohol by retrosynthetic analysis. In this figure, you can see this is a primary alcohol. If you disconnect this carbon alkyl bond, there is generation of the carbanion part which will come from organolithium compound, and this part will come from the carbonyl group. This is nothing but formaldehyde. Now, if we have to prepare a secondary alcohol or we have to plan the synthesis of secondary alcohol, then there are two routes possible. Look at this molecule, this is the secondary alcohol. Now, if we disconnect this part of the molecule, then R dash will become the part coming from organolithium compound and rest of the molecule will form the carbonyl compound. But if instead of this R dash we disconnect this carbon R bond, then there will be this carbonyl group and alkyl lithium compound will be generated from this part of the molecule. With the help of example, we will show you how a secondary alcohol can be prepared. In this particular example, this is 2-hexanol. This is a secondary alcohol, and since we have already discussed that in case of secondary alcohol, two routes are possible for planning of this synthesis. So, one route will be when we disconnect this carbon-carbon bond. As a result, methyl lithium will be the organolithium compound and the carbonyl compound will come from this pentanol. So, pentanol and methyl lithium when react will form this 2-hexanol. The other route will be where we can utilize or we can break this carbon-carbon bond. As a result, this butyl lithium will be the organolithium part, whereas CH3CHO, that is acetaldehyde, will be the carbonyl part. Now, if you look at both the routes, you will find that in both the cases we are preparing a secondary alcohol from an aldehyde other than formaldehyde. This pentanol is also an aldehyde. Similarly, acetaldehyde is an aldehyde other than formaldehyde. So, for the preparation of secondary alcohol, the requirement is the alkyl lithium and an aldehyde which is not formaldehyde. Now, we will discuss the synthesis of tertiary alcohol. Here, three routes are possible for the synthesis. If we disconnect this carbon R bond, C and R bond, these two moieties will be required. You can say that this part will be generated from carbonyl molecule and this will be from the alkyl lithium part. In this case, this carbon R dash bond has been broken, and in this case this carbon and R2 dash part has been broken. So, three routes are possible for the preparation of tertiary alcohol via this retrosynthetic analysis. We will discuss this with the help of an example. The example we are taking is of 2-phenyl 2-butanol. 2-phenyl 2-butanol is a tertiary alcohol. Route 1 for the preparation of 2-phenyl 2-butanol is starting from methyl lithium and 1-phenyl 1-propanone. That is, we are disconnecting the molecule from here. As a result, we are taking a ketone and methyl lithium. In the second route, we are disconnecting the molecule from this carbon-carbon bond. As a result, we start with ethyl lithium and acetophenone to generate the same molecule. In route 3, we disconnect the molecule along this carbon and phenyl bond. If we break the molecule from here, then the ketone will be 2-butanone and phenyl lithium will be the organometallic compound which will be used for the synthesis of this tertiary butanol. So, with this discussion for the preparation of primary, secondary and tertiary alcohol via reaction of organolithium compound with appropriate carbonyl compound, we can see that we can prepare very complex molecules if we know how to start or how to break the molecule or from where to break the molecule to prepare the appropriate end product. And that is why this planning or this retrosynthetic analysis is very useful in synthetic organic chemistry. We will now sum up the present lecture, in which we have introduced organolithium compound, we have done the bonding in organolithium compound, and after that the preparation of organolithium compound. We have discussed reactions of organolithium compound where they act as Bronsted bases. We have discussed the reactions with compounds which have active hydrogens such as alcohol or carboxylic acids. Then we have discussed reaction with carbonyl compound. We have discussed the preparation of alkynyl organolithium compound and their uses in the synthesis of alcohol. Then we have discussed the reaction of organolithium compound with oxygen, with epoxide, with esters and with carbon dioxide. And finally, we have discussed the retrosynthetic analysis in detail for the planning of synthesis of primary, secondary and tertiary alcohols by this method. So, this lecture concludes the unit of organometallic compounds, in which we have discussed organomagnesium compounds, which are also called Grignard reagent. We have discussed organozinc compounds, we have discussed organolithium compounds. All these categories, all these types of organometallic compounds are very useful in synthetic organic chemistry. The only difference in these type of compound is their reactivity, and you already know that reactivity depends on the electropositivity of the metal attached to carbon. Higher the electropositivity, higher will be the polarity of the bond and higher actually will be the reactivity. So, I think with all these lectures on